the outset, I am very much thankful to NITT here Chandigarh to give me this opportunity to deliver a lecture on bacteria foraging and its engineering application. Before going to the detail of bacteria foraging, I want to emphasize on optimization. What is an optimization? Everybody knows. That is either to find the maxima or a minima of a chord. The chord or a function is having a upper limit and a lower limit. So we want to find out either the upper limit or the lower limit. So depending on your problem, basically the function to be optimized differs. For example, if I am in electrical domain, I can optimize the energy production. I can optimize the control efforts. Similarly, in your electronics domain or image processing domain, you can optimize the best you can reduce the noise. You can optimize the maximum bandwidth available. Like that, you can formulate different types of problem. So depending on your problem, the most important thing is formulation of the cost function. If that is correct, then the algorithm will perform to its optimum. Otherwise, you will not get the proper result. Okay. Now, these are some functions. The function can be a constraint or a unconstrained one. Means you can have some limitations or you may not have some limitations. For example, minimize the function x square plus 2y square. What is the limitation? X must be greater than 0. So this is a constraint. Similarly, you can have many constraints over the optimization function. So these constraints are to be properly put into the cost function formulation. It is not that you should go by the if then rule. You should not optimize the function that if x is negative, then don't do the optimization. But instead, you should keep that as a constraint in the cost function. Then what will happen? The speed of convergence will be much faster. Okay? This you can do by if then rule also, but don't do by if then rule. Instead, put it as a penalty over the cost function. That is called as penalty approach. So now, see, the function that is to be optimized may have many modes. What do you mean by modes? For example, if I will come to this function, see, so here you see this is a minimizing point or a minimum, as well as here there is a minimum. Now when I will tell that find the minimum of this function, then I should come to this point, not to this point. This point is a local minimum and this is a global minimum in the universe of discourse. This we always find the minima within a universe of discourse, that is the variation up to what you are interested for. So here you may think that from -5 to +5 I am having the universe of discourse, and within that zone I want to find the minima. Okay. Now when this type of function is there, means there are many minima or many maxima, and you want to optimize or you want to find out either the minima or maxima, then the gradient descent will have problem. Because the most conventional approach for finding the minima, that is optimization, minima or maxima anyway, is gradient method. What is gradient method? We all are using this genetic algorithm, bacteria foraging, particle swarm, all things. But what is the conventional one? The conventional one is the gradient, means find out the slope, dy by dx, see whether that slope is coming positive or negative. Suppose if you are maximizing and you are getting a positive slope by variation of x by increment delta x, then move in that direction because it is a maximization. Similarly, if it is minimization, move in the opposite direction if you are getting a negative slope. So that is called as gradient method. Now this gradient method is having one limitation. Why it is not coming? Let me see. So what is the limitation? It depends on the initial condition. This is a gradient descent program which I have written in MATLAB, and this is the function, and I want to find out the maxima. Here how many maxima? 1, 2, 3 maximum are there, and this is the global maxima that I want to find out. So I will start from an initial point, initial gas point, and I put 3 here. I don't know where is the maxima is there in the system. So I will start from a random point. It may be 3, it may be 4, it may be 5. So at the first instance I put 3. Now I will run the program. See, it is moving and going to the maximum point. So this value if I will take, then I will get the maximum. Now suppose I am changing the initial point to 5. See, I am starting here now from 5, and now I will go for the optimization. Sorry. See, it will be trapped to the local minimum. So this indicates that the gradient descent method or the slope method is dependent on the initial conditions. If your initial condition is proper, then you will get the maximum, that is global maximum, or you will miss it. So now since you do not know the global maximum, where it is lying, the gradient descent will be in problem. Because suppose this is giving me this result I am getting, I will be happy with that because I don't know where the global minimum is. Here since I have plotted a function, you know that here the global is coming. But for a real time situation, I don't know where the global minimum or maximum is. Therefore, we go for all these new technique, that is stochastic optimization or population based technique. So now let us solve the same problem or another basically different function, but with stochastic optimization. Here I started with many random numbers. See, what is the global peak? Here there is a global peak, and I don't have any number exactly lying here. This is one number which is around that. By chance it has come due to the randomization, but it may not also come. Now I will go for whether it is GA or bacteria foraging or whatever it may be, in producing different random numbers. So in each generation I will produce new set of random numbers. This is generation number 1, and you will see that all are migrating towards the peak, and all the points becomes a single point. So this particular one is giving me the global maximum. Therefore, we are interested for this type of optimization strategy. And in this optimization strategy, different algorithms has been proposed, and the most commonly used is the genetic algorithm, which is widely used, and it has also come up to a industrial standards. After that, if you see the PSO, maybe the another one which is next in the number after genetic algorithm, and the bacteria foraging is recently coming up, which is also a stochastics or population based optimization strategy. So these things the speaker in the first session has already pointed out a little bit. The foraging strategy of any living beings. The foraging means search for food, and any living being wants to eat more and more so that it will be survived in the society. And each living being is having the inherent characteristics to increase its population, or so to say, to maintain its population. So that maintaining the race is coming with reproduction strategy. And in case of this bacteria foraging, there is another one that is called as elimination and dispersal stage, in which the bacteria may be dispersed from one location to another location due to some undesired situations. So with these three things, that is chemotactics, which in the morning session he has already mentioned about, reproduction and elimination dispersal, this bacteria foraging algorithm is formulated. Now here, see, any bacteria when it is moving inside our E. coli, that is intestine, E. coli bacteria, they swim in our fluid present in the intestine. So that swimming, when the flagella is in this direction, means they are clubbed together, it moves in a particular direction. And if it is randomized, means if it is moving in random direction, then it can have a random motion. That is called as tumbling. So with the help of swimming and tumbling, the bacteria moves inside our body for searching the food. So now, because some of the students are using these bacteria foraging, so let me go into the mathematics part other than going just a lecture type of thing. Okay. Now here, in the first chemotactic stage, as I mentioned, it is comprising of swimming and tumbling. From this chemotactic stage, now you will decide which bacteria is successful for reproduction, because it is survival of the fittest. From one generation to the next generation, the fit one will only propagate, not the other one, right? So the chemotactic stage is nothing but, suppose this is the random initial start, then you find out another random number of the same dimension multiplied by a coefficient. Because why I am multiplying a coefficient is, in the MATLAB, because we do use MATLAB very frequently, the rand one is coming between 0 to 1. The parameter that is to be optimized may not be in the range of 0 to 1. If it is in the 0 to 1 range, you may put C is equal to 1. If it is not within 0 to 1, then you have to go for a scaling factor, either upscaling or downscaling. So therefore, I may need a C here if I am using the rand command of the MATLAB. Okay. So now I multiply this and I am adding this to the initial position. Now when I am adding this is a new random number again. Now I have already found out the cost function for this random number, which is the first one. Now I am getting a new one at the j plus 1 state. I will find out the cost function for this one. I will now compare whether this present one is less than the previous one or greater than the previous one. If I am going for a minimization strategy and the present one is lower than the previous one, that means the random number that I have added here is correct, or it is in the proper direction, which is reducing my cost, and I am going for a minimization. I am not going for a maximization. Okay. So this addition is now perfect. So what the bacteria will do? It will decide to swim further because it is getting more food. Cost function less means it is indirectly telling more food. So go on adding this random value which you have found out for some time, 1 or 2 or 3 steps. That is called as swimming length, and that is decided by you. What iteration, what number of iterations you will give for swimming. Okay. Now once it is completed that number of iterations, then intentionally again change this random number, even if the cost function is going to be lower, and that constitutes a tumbling now, because we don't know, there is a reduction in cost function no doubt, but that reduction may lead to a local minimum. It is reducing just like in the gradient one, but it may be a local minimum. So don't go much in depth wise in that direction, otherwise you may be trapped to a local minimum. So change this random number after some time. That is called as tumbling. So tumbling can be achieved or can be coming into picture in two cases. One, either the swim length has been over whatever you have defined, or the random number which you have found initially may not give you this j less than the previous one. So in these two cases, tumbling will occur in the algorithm. You have to find out a new random number. So this completes one chemotactic stage. So in one chemotactic stage, there are two sub stage. One is swimming and another is tumbling. So if you define the chemotactic stage to be of 10 iterations, and if you define the swimming of 7, then up to 7 it will go on in the swimming direction, means same random value will be added, and after 7 another new will come, and that will continue up to 10, or that may also change depending on this decision, whether j is greater than or less than. Okay. So this completes your chemotactic one. So in one chemotactic, how many cost values you are getting? Suppose I am taking 10 iterations, then I will get 10 cost values. Each iteration will give me one cost value, means cost function value. Cost value means cost function value. So now I am having 10. So like that, if there are 10 bacteria, it will be having a matrix of 10 by 10. So the issue is now you have to define which is the best bacteria, because the best one will survive for the next generation. Survival of the fittest. In case of genetic algorithm, I hope all are exposed little bit to genetic algorithm. What do? You take, if you are minimizing, you just arrange them in a proper manner such that the minimum one will be the top and the maximum one will be the bottom, and you replicate the thing, or you divide in 50%, survival of the fittest, 50% will die and 50% will go to the next generation. Similarly here, what you will do? Now you are having 10 in the chemotactic, 10 in the bacteria. I have to choose a proper strategy. The Pacino has proposed that go for the summation. Sum all the cost function of one bacteria. Suppose bacteria number 1 has traveled 10 chemotactic, so then you sum all these values. Whatever value you are getting, that is the value corresponding to bacteria number 1. Similarly, you calculate the 10 and then you go for either maximization or minimization, ascending order or descending order, depending on your strategy. Okay. So my first paper that has come in IEEE evolutionary computation, this one, if you see, that is in 2005. Suppose, see, first value is 1, next value is 1, or next value is 2, next is 3. Sum becomes 6, but the minimum is 1. Bacteria number 2, all are 2, 2, 2. Or let us assume first is 1, 2, 4, that means 7, 1, 2, 4. Next is 2, 2, 3, or 2, 2, 2, let us assume. So 2, 2, 2 is 6, first one is 7. So now it will choose the second one, because 2, 2, 2 is 6, but the minimum is lying in the first one. So I am missing the first, that is the cost value is 1. So therefore it is going increasing direction. Then we propose the new method that has also come in the IEEE transaction, I think in 2006, that is power delivery, where we have used another strategy, means optimization problem, that I will come to later on here. Okay. So if you carefully see, it may be visible, otherwise I will point it. This is bacteria foraging and this is GA. Okay. So then we switched the method or changed the method, that don't go for the summation one, but go for the minimum one. So in the same chemotactic, for bacteria number 1, you find the minimum and define bacteria 1 cost as the minimum of that. Similarly for 2 you find the minimum, then you go for the ascending or descending order depending on your problem. And in that we avoided that zigzag path, and it becomes much faster than that of the GA. This is the GA and this is the bacteria. And the elimination dispersal is nothing but changing suddenly the value of a bacteria to another new value, that is using again a random number. You intentionally, with a probability no doubt, just like mutation and crossover in genetic algorithm, you suddenly, if that probability is crossing the value, suddenly change one of the bacteria that is randomly chosen to a new value and see how it is performed. So this is all about the bacteria foraging strategy to find out the minimum or maximum value. If you remember the thing that in the first session has been presented, that it is a single population, means in the population there are only one value. In fact, in my 2005 paper in IEEE, if you see, I have also done the thing with single bacteria, a real-time implication, a real-time implementation. How much, means how can I use the genetic algorithm or particularly bacteria foraging I have done in that paper in real time. When you come to the real time, it becomes the time is very, very important. In how much time, how much computational time you are able to get the minimum. So that has been achieved with taking the single bacteria as a case, and that has been reported in that paper, particularly this paper, this harmonic estimation paper. Okay. So I have used the bacteria foraging for optimization of around 5 to 6 problems. One is the harmonic estimation, means here I have to estimate the amplitude and the phase angle under a noisy situation. This is the noise. So I formulate this function in the MATLAB by intentionally writing this equation and adding a noise to it. So I assume that that is my samples which I am getting from the real time operation. Then I go for a laboratory test also. Now this function, this a is multiplied to a sine function. This sine function is a nonlinear function. So this phi n estimation becomes a difficult task, whereas an estimation is not a very difficult task. This an can be estimated with simple least square, which has been very much established in the theory. Just take the inverse of the matrix, you will get the value of an. But this phi n cannot be estimated like that. So I have used the bacteria foraging to give me phi n, and an has been calculated through simple least square strategy. And iteration by iteration, new phi n comes into picture, and new an is calculated, and ultimately it matches to that of the sample value, such that the error becomes 0. So this is the problem that I have tackled with bacteria foraging algorithm. So I am not going into detail of this. This is the relationship for calculating the A. And these are the results that has been reported. These are the 5 harmonics present in the signal. If you take a power system or the circuit like this, which is having a diode and a load, then you will get, no doubt this is a 3-phase system, and you will get these harmonics. So forget about these harmonics. It is having a waveform like this, a distorted waveform. That is important. How it is generated is not very important. So this distorted waveform is having some harmonic amplitude and some phase angle that is to be properly estimated. Now when noise is added, you see the distortion becomes more and more, and it is to be estimated from this noisy signal. So I use genetic algorithm, then conventional bacteria foraging, then fuzzy bacteria foraging. In the fuzzy bacteria foraging, what I did, I vary the C, that is the coefficient, with certain fuzzy rules. The real rules has been formulated from error. If you see that paper, it is clearly written. I don't remember exactly the rule what I have formulated at that time. So it is clearly written there. So with that fuzzy rules, I get quite better performance compared to that of both GA and the conventional bacteria foraging. Even the conventional bacteria foraging, with that approach, even with summation of all the value, it is better than the GA in the convergence. And here if you see, I have taken number of J evaluation in the x-axis. Why I have taken that is also a issue. Generally if you see, it is number of iteration, not number of J evaluation. Intentionally I have taken this because I am now comparing GA with another technique. The iteration in GA is not same as that of iteration in bacteria foraging. So I take the parameter to be the number of evaluation of the cost function as the issue, because that takes the maximum time in a real problem compared to that of the algorithm. So these are some of the results which has been reported, that is there in my paper also, you can see. So no need to go for. Now I have also used this bacteria foraging technique for another electrical problem, that is active power filter. I am not going into active power filter because you feel bored about that. But the issue is, here I am having a PI controller, a simple PI controller which is having Kp and Ki, 2 parameters. I have to find these 2 parameters such that my response will be good. So I formulate a cost function. So the cost function that I propose for this one is error square. Suppose when I am having, what is the function of a controller? Why I am discussing this problem is to emphasize the creation of the J function, which is very, very vital in case of any stochastic optimization. Now here in this control problem, my aim is to reduce the overshoot and undershoot. When I am having, suppose this is the steady state, I am giving a disturbance, then it will may reduce and some oscillation and go finally to the steady state. So, since I am designing a controller, my aim is to reduce. So, my issue is here, since it is a designing of a controller, to reduce this overshoot undershoot, and as far as practicable, the settling time should be small, so that my response is better. So, I take a performance which is error square. I just add on all the error square, so that if the overshoot and undershoot is big, my cost function will be larger, otherwise my cost function will be lower. So, with this aim, I formulated that it should be error square. Now, as I told that there should be also a settling time in the issue, I multiply a t there, because if the t is larger, suppose a error is occurring at t equal to 5 seconds and same error is occurring at t is equal to 1 second, which is dangerous? 5 seconds is dangerous. I cannot tolerate larger error after large disturbance, means after a large time I have allowed, but I can tolerate that when I am having less error. Therefore, I multiply the t here. So, this is very vital for any optimization problem. You have to judiciously decide about this cost function. Just like I give an example now for a control problem, my aim is to reduce the error, so I put error square. My aim is to reduce the settling time, so I multiply by 2. Like that, you have to decide about your aim and formulate the cost function. Now, here I am having 3 operating conditions, and my controller should perform correctly in all the 3 operating conditions, at least satisfactorily, not maybe optimized, but satisfactorily in all the operating conditions. So, if I am optimizing with only one condition, it may perform poor in other 2 conditions. I don't know. So, what I did, I take J1, J2, J3 and add them all to formulate my final cost function. So, my final cost function is a sum of all the 3. So, like that, you may have 6-7 aims and 6-7 operating conditions. You don't know. So, that is to be taken care properly. So, once it is finalized, then you can optimize the value for Kp and Ki. Here 2 parameters are there. So, my bacteria will comprise of 2 parameters. Basically, that P matrix, if you see the code of Pacino also, that P matrix will now contain 2 values. If it is 10 parameters, it will contain 10 variables. Okay? And this is the performance. Similarly, there are certain other applications which I have. Here there is another problem in which I have compared CGA, that is conventional GA, DGA, that is differential GA, and that is another is bacteria. So this one gives me the best performance compared to the other. No doubt DGA gives better than the CGA. So like that, this has been applied to different problems and we have obtained the final optimized. So I think this completes my talk on bacteria foraging and its application to different problems. In fact, now recently I have sent another one, that is bacteria swarm algorithm, in which I have modified the swarming strategy of the bacteria foraging algorithm that has been proposed. Okay. So any question?
In bacteria foraging, how you are taking care of the situations when the parameters are trying to cross the boundary?
Yeah, that's what I told at the beginning of my talk, that the constraint, basically you are telling
that you have to add in the cost function itself?
Yes, that I have done like that. That is constraint handling. Just I have taken some, suppose 1000 into, suppose my x should be within 2, let us say,
Okay.
plus 2. Okay. So 1 minus sin SIGN 2 minus x. So if x is exceeding 2, then you will get a plus or minus sign. 1 minus that, either it will be 0 or it will be a positive quantity. Either it will be 0 or it will be 2. Then multiply by 1000 gives me 2000. So I am heavily penalizing the cost function. That's why I have taken the boundary universe of discourse. But some of the papers has also referred regarding this. You should not go for a very rigid boundary. You should go for a soft boundary if it permits you. For example, in our power system, suppose my power flow should be 10 megawatt. If it becomes 10.5 megawatt, it doesn't matter to me much. So if I am putting a very rigid constraint of 10 megawatt, I may not get a very good optimal result. But let me allow a bit. So if your problem allows that, that depends on the problem. Just like in the morning sessions you was pointing, this resonance frequency has to be pinpointed like that, then you cannot allow any deviation. If your problem allows that deviation, then you make the constraint a fuzzy one. Don't make it a rigid one. That is fuzzy constraint handling.
Is the choice of the cost function, suppose for example E square,
Yeah.
or E, is it is that depend on the time of computation also? If you are taking E square or E,
Type of computation.
time of computation.
Time of computation.
That means to get an optimized value, if you are taking E square.
No. See, that I don't think hamper in the convergence.
Okay.
But if your E calculation is taking some time, then E square may take some time. Therefore, I am telling the most important part is the cost function calculation. The J I have to calculate. So this J calculation itself is the largest time consuming factor compared to the running of the algorithm. Therefore, if you see, I think like that. You may have some better suggestion. This is number of J evaluation. I am not telling about number of iterations. Suppose in case of GA, you take a 10 population. So in each iteration, how many number you are calculating? How many times? 10 times. J calculation is coming 10 times. Initially you take a 10 population, calculate the J, go for crossover mutation, generate another 10, calculate the J, this completes one iteration. Next iteration again 10 new you are calculating. But in case of bacteria foraging, suppose if you take 10 population, 10 bacteria, 10 chemotactic, in one reproduction itself you have calculated 100 times. So the iteration of bacteria, if I will make this one iteration, then my bacteria foraging will be converging here. Because in one iteration you have calculated 100 times your J. Instead in GA you are calculating 10 times. So that is, therefore I have taken here number of J evaluation.
If you take a single bacteria, that will be suitable for real-time applications.
Yes.
Now, have you applied this BFO to any real-time applications?
Real-time application exactly I have not applied, but if you see that paper, I have proposed a thing. What I have done, I took the data from a data capturer, means a harmonic analyzer which is having A to D conversion, and I take a basically diode bridge. So I am getting a rectified waveform. A rectified waveform will contain harmonics. So I take that waveform as my samples. So I connect a data capturer and I took that sample, take it to my computer, run my bacteria foraging algorithm, and I calculated the time in which it is giving me the up to satisfactory result. In real time, you should not think that you will get the optimal,
That is millisecond
because
time.
optimal means whether it is 10 to the power minus 12 or 10 to the power minus 13 or 10 to the power minus 2. It is a varying thing. So in practice, if you see, suppose if I am reaching a 10 to the power minus 2 percentage error, then it is quite satisfactory. I need not go beyond that. With that approach, I keep a limit over that. I think I have mentioned that in that paper also. I think I have put 10 to the power minus 2 as a percentage. This much percent. If my J is reducing to this much percent, I am happy. I need not go anymore. So I stop there and I converge that up to that error in some millisecond. But if you go to the DSP processor, you may get even less than that. I have gone by MATLAB platform. Thank you for this lesson sharing to me.